Okay, so when we use the zero address instruction, just when we use add, actually it uses the stack, that is the top of the stack, the top and the top of stack minus 1. These two elements will be popped out of the stack and they will be added and they will be kept in the top of the stack. For example, if stack contains these elements 2, 3 and 5, it will pop out 5 and 3 from the stack and the new top of the stack will be 8. Okay, so this is what the zero address instruction will do. And risk instructions, generally in a risk processor the number of instructions will be more than other processors, because they will separate the load instructions from the load and store instructions from other instructions. In some instructions the load and store may be merged with the actual instructions, so those will be separated out when we use a risk based system. So let us see how this particular instruction is executed in various uh, instruction formats. With a three address format, let us see how it is executed. So in a three address format, this instruction a plus b star c plus d will be executed something like this. First it will perform add r1 comma a comma b, which will add the content of memory location of a with the memory location of b, and the result will be stored in r1. And then it will add the content, add r2 comma c comma d, which will add the content of memory location c with the memory location d, and that result will be stored in the register r2. So now a plus b is available in r2 and a plus b is available in r1 and c plus d is available in r2. These two things should be multiplied. So multiply x comma r1 comma r2, which will multiply r1 with r2, and that result will be stored in the memory location x. So this is how this instruction can be executed using three address format. The same instruction can be executed using two address format, something like this. Move r1 comma a. This will move the content of memory location a to the register r1. Add r1 comma b. This will add the content of r1 with the memory location b, and the result will be stored in r1. So now we have completed a plus b. So with this a plus b was done. Similarly c plus d also will be done. Move r2 comma c. This will move the content of memory location of c to r2. Then add r2 comma d, which will move the which will add the content of r2 with the content of the memory location of d. So with this c plus d is done. So a plus b is now available in r1 and c plus d is available in r2. These two things should be multiplied, which will be done by using the instruction multiply r1 comma r2, which multiplies r1 and r2 and stores the result in r1. Move x comma r1. So this will move the content of r1 to the memory location x. So this is how this instruction can be executed by using two address format. The same instruction can be executed in using one address format, use something like this. Load A. This will load the content of the memory location A to accumulator. Add B. This will add the content of the memory location B with the current content of accumulator, and the result will be stored in the accumulator. Now the result of A plus B is available in accumulator. Store T. This will store the content of accumulator to the memory location T. means a plus b is now stored in the memory location t. Next we should perform load C. This will load the content of memory location C to the accumulator. Add D. This will add the content of the memory location D with the content of accumulator, and the result will be stored in accumulator. Multiply T. This will multiply the content of T. So T actually contains A plus B, that will be multiplied with the content of accumulator, which is nothing but C plus D, and the result will be stored in accumulator. So now the final result is available in the accumulator, and that can be stored into any memory location by using store X. This will store the content of accumulator result to the memory location X. Same instruction can be executed by using zero address format, something like this. Push A. This will push the content of A to the stack. That is, it will push the content of memory location A to the top of stack. B, which will push the content of memory location B to the top of stack. Next, add. So when add is executed, that is when any arithmetic or logical operation is executed, the top two elements of that stack will be popped out. So this will pop up B and A, and both will be added, and the result will be stored in the top of the stack. So this will be pop out B and A. Top of stack is B, that will be popped out. Top of stack minus 1, that also will be popped out, and that result will be stored in now in the top of stack. So now top of stack will be A plus B. A plus B. Next, push C. So this will push C, content of the memory location C, to the top of stack. Next, push D. This will push the content of the memory location D to the top of stack. Then add. So again it will pop the top two elements of the stack. Top of stack and top of stack minus 1. That is, it will pop out D and C, and it will add, and then it will keep it in the top of stack. So now top of the stack will be D plus C, followed by that it has A plus B. A plus B. A plus B should be multiplied with D plus C. So again we perform multiplication, which will pop out D plus C and A plus B, and these two things will be multiplied, and that final result will be stored in the top of stack. So that final result, which is nothing but A plus B plus A plus B star C plus D. Now that will be stored here. And pop X, so which will take that final result out, and it will store in the memory location X. So this is how this instruction can be executed by using zero address format. Same instruction can be executed in a RISC machine, something like this. Load R1 comma A. This will load the content of memory location A, register R1. Load R2 comma B. This will load the content of the memory location B to the register R2. Load R3 comma C. This will load the content of memory location C to R3. Load R4 comma D. This will load the content of memory location D to R4. Now all the contents of the memory location were moved to the appropriate registers. A is moved to R1, content of B is moved to R2, content of C is moved to R3, content of D is moved to R4. Add R1 comma R1 comma R2. This will add R1 and R2 and store the result in R1. So now the result of A plus B is available in R1. Add R3 comma R3 comma R4. This will add R3 with R4, and the result will be stored in R3. It is C plus D is now available in R3. Multiply R1 comma R1 comma R3. This will multiply R1 with R3. That result will be stored in R1. Store X comma R1. So actually that final result is now available in R1, which is nothing but A plus B into C plus D. And that is now stored into that memory location X. So basically the RISC instruction, it will separate out all the load and store instruction. You cannot merge the load and store instruction with other instructions. So that is what the RISC computer will do. Okay, fine. So in most of the instructions we are using registers. So basically the usage of registers makes the processor work faster, and also the size of the instruction will become small. Okay, that is when you use register, you need not access the memory location directly, and 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 the registers can be accessed with less number of bits. If a typical computer has 32 registers, okay, if a typical computer has 32 CPU registers, then all these 32 registers can be accessed by using just 5 bits. So registers are also basic memory locations in CPU. That is, they are these are some locations which are available in the CPU. So they also have address. So they should be accessed by using some address. For accessing this, just 5 bits is enough. Using 5 bits, you can access 32 registers. Okay, because 2 to the power 5 is nothing but 32. Okay, so which will increase the speed up, which will speed up, and also the uh, the movement of data between processor and main memory will be reduced, so that the speed will increase. The next thing that we'll be discussing is instruction execution and straight line sequencing. That is, generally in a computer, the instructions will be executed in a straight line. That is, the instruction will be executed in one by one fashion. Okay, until and unless it is not disturbed by a loop or by an control statement. So let us assume that, so this is the structure of the memory. Let us assume that each location in the memory is of size one word, where one word is equal to 32 bits, where one word is equal to 32 bits, which is nothing but 4 bytes. It's nothing but 4 bytes. Okay, so if ith instruction, so if a particular instruction is available in ith byte, if a particular instruction is available in ith byte, then the next instruction will be available in I plus 4th byte, because each instruction needs 4 bytes, and the next instruction will be available in I plus 8 byte. Okay, so let us discuss a simple case where there are just 3 instructions in a program statement. So the first instruction is move a comma r1, move a comma r0, move a comma r0. Okay, this will move the content of the memory location a to the register r0. Then add b comma r0, which will add the content of the memory location b with the content of the register r0, and the result will be stored in r0. Then move r0 comma c. Whatever the final result available in r0, that is moved to the memory location c. So this is a typical program with only 3 instructions. So this program, how it is executed? It executed in sequence, line by line. First statement, then the next first instruction, then the next instruction, which is obtained by adding the appropriate word size, that is 4 byte. So first instruction is starting at ith address, then the next instruction will start at I plus 4th address, then I plus 8, and so on it proceeds. Okay. Now let us consider so this program basically adds two values a plus b and store that result in the memory location C. Let us assume another program where we want to add a sequence of numbers. Say we want to add all these numbers. We want to add number 1 with number 2, 3, number 4, number 5, number 6 up to number n. And that final result should be stored in this location sum. Okay, the value in the location number 1 should be added with number 2, that should be added with number 3, number 4, and it goes on up to, and that final result should be stored in the location sum. So how can we write a program? So generally we have to write this type of program using a loop, because there are many numbers to be added. But let us initially, for understanding purpose, let us see the version of a program without loop. Okay, so first what we are doing, move number 1 comma or not. So this will move the value which is available in the memory location number 1 to or not. Okay, that is this location, whatever the value available here, that will be moved to or not. Add number 2 comma or not. This will add the value that is available in the location number 2 with or not. So or not contains number 1 and the result will be stored in or not. So this will basically perform number 1 plus number 2. Okay, then again we are doing add number 3 comma or not. So previously or not contains this number 1 plus number 2. So the next statement we are telling add number 3 comma or not. That is, we are saying that add the value of number 3 with or not. Or not is what? N1 plus N2. So we are telling that you perform N3 plus or not, which is nothing but N3 plus N1 plus N2. So that will be new or not. That will be the new or not. Okay, that is R0 register. So this process continues. The next instruction will be add num4 comma or not. So which is nothing but the number 4 will be added with or not, with the content of the register or not, which is nothing but number 1 plus number 2 plus number 3 plus number 4, and that is the updated value of the or not. So you keep on proceed as long as how many numbers are there, right? So this is how you have to write this program. But generally, so this is the actual understanding where each of these instruction occupies, the first instruction occupies ith byte address, then the next will occupy I plus 4th address, then I plus 8, so on and so forth. Okay, but generally we can't write this many instructions because we don't know what is n and how long we should do this. So we will use a for loop. We'll use a loop. Okay, so if you use a loop, then this program will be modified something like this. So move n comma r1, where n is the count how many numbers you want to add, that is n, and that is stored in some location in the memory. So this small n represents how many numbers to be added. So if n is 5, it means that we want to totally add 5 numbers. Okay, that is num1 plus num2 plus num3 plus num4 plus num5. Okay, that is stored in n. That whatever n that is now stored in R1. So R1 now contains, in our case, R1 contains 5. Okay. Then the final result should be stored in R0. So we are clearing R0 initially. It is R0 is made to 0 because we want to make sure that no garbage value is stored in R0. So that we are clearing it to 0. Okay. Then comes the actual addition part. Here we are not writing the exact code. Rather we are telling what to be done. Determine the address of the next number and add the next number to R0. So the address of the next number is nothing but this one. Identify that and add that with R0. So what will become? R0 will become, the next address is nothing but the value of num1. So R0 will become num1. Whatever content in num1, that will be R0. Then what we are doing? Decrement R1. So previously R1 is 5. Now it will become 4. Then we are checking branch greater than 0 loop. What is greater than 0? So it means previously we performed some operation is the result of that operation is greater than 0 or not. That is what this branch checks. Yes, it is greater than 0. Previously we performed this decrement operation which decremented 5 to 4. The final result is greater than 0. If it is greater than 0, go to loop. That is what it says. So what is loop? This instruction. So again the control will come here and again this part will execute. That is determine the next address and add that to R0. Next address is what? N2. That will be added with R0. So it will become R0 is equal to N1 plus N2. So previously that is previous R0 plus N2. Previous R0 is nothing but N1. So the current R0 will become N1 plus N2. Current R0 will become N1 plus N2. Again it will now again decrement R0. So this will become 3. This will become 3. Okay. So this will become 3. So again it checks whether branch greater than 0. Yes, branch is greater than 0. So once again it will go back here. So like this the process continues. At one point this will become 0. So at that point it will check whether branch greater than 0 or not. No, it's not greater than 0. So it will come here. By that time R0 will have N1 plus N2 plus N3 plus N4 plus N5. And that result will be stored in sum. Okay. Right. So here the flow is getting disturbed. Okay. So normally we know that the address of the next instruction that is to be executed will be available in the program counter. Okay. And the instruction execution generally contains two phases. One is called as instruction fetch. During this phase, during instruction fetch, the whatever the address that is available in the program counter, that instruction, the instruction that is referred by the program counter, okay, the instruction specified by the address given in the program counter, that will be moved to IR instruction register. That will be moved to the instruction register during the instruction fetch phase. Okay. So the particular instruction that is referred by the program counter will be moved here. And during instruction execution, the second phase is instruction execution. During instruction execution, that particular instruction will be executed. Okay. But this execution itself may have multiple steps depending on the type of the processor. Like it may first perform instruction decode. During that time it will try to understand what that instruction want to do, the add or multiply or divide or what. Then operand fetch, during that it may fetch the operand, then instruction execute, then execute and store the result. Okay. So during this execution period, this PC will again increment to the next address generally. Okay, so that again when the processor comes and check the PC after executing this current instruction, program counter will be pointing to the next address. So the instruction in the next address will be fetched. Like that it continues. But when there is this type of branch instruction comes, the program counter will not just follow the sequential flow. It may follow a different flow. So here when the branch is greater than 0, the program counter value will be replaced with the address specified in this loop. Okay. So it won't follow the sequential flow, rather it follows a unsequential flow. Okay. When it is not greater than 0, at that time it follows the sequential flow. Okay. That is when the particular condition fails, then it follows the sequential flow. If it is true, it does not follow the sequential flow. Then conditional codes. Here this greater than 0 is a conditional code. Like that, what are the other conditional codes we have? These conditional codes are also called as conditional register or status register. Like that we have negative. It means is the result is negative or not. If the result of the arithmetic operation is negative, then what to do? If it is negative, then loop. Okay, if the result is 0, then loop. So here it is 0. If it is greater than 0, we said it is. So GE means we can say great, or GZ means greater than 0, then loop. Okay, different processors will have different instructions, right? So V means overflow. If the result of the arithmetic operation results in an overflow, then the loop will execute. Similarly, if the result of the arithmetic operation results in a carry, then it may uh, change the path, that is, the loop may execute. Okay. So these are the other conditional codes. Okay, fine. Let us stop here.